Okay, so hi everyone. So welcome back to yet another video. So today in this video I will be discussing about this codeforces problem, tree with maximum cost, and it has came in div 3 around 527, and this problem is rated 1900. So we will see how we will approach this problem and solve it using the concept of dynamic programming on trees along with the technique we generally call as rerouting, right? So let us start with this problem. So the problem reads like this, that you are given a tree consisting exactly of n vertices. So we just have a tree with n vertices. Since it is a tree which is obviously undirected, so it has n minus 1 edges also, right? And each vertex of this tree has a value assigned to it. So each vertex has a value. Let distance xy be the distance between the vertices x and y. The distance between the vertices is the number of edges on the simple path between them. Let's define the cost of the tree as the following value. First, let's fix some vertex of this tree. Let it be v. Then the cost of the tree is summation of this term. So we will later discuss what is this term actually is. And finally, your task is to calculate the maximum possible cost of the tree if you choose v arbitrarily. So in the input we will be given with number of vertices in the tree, and in the second line we would be given with the values of each vertex, and then we have to take the input for n minus 1 lines uh, consisting of two integers u and v, and this will form a tree, right? So it is guaranteed that the given edges form a tree. So it means that it will exactly have n vertices and n minus 1 edges and no cycles, and it will be all connected. So in the output we just have to print one integer which will denote the maximum possible cost of this tree if we choose any vertex as v, and it has to be the maximum. There are two examples provided. So let me explain you these examples and how this output is coming for each one of them. So this is the very first example given in the problem statement, and as you can see this is the resulting tree, and each vertex of this tree is having some value associated with it, right? Like the first vertex has a value 9, the second vertex has a value 4, and so on. And the expected output for this example is 121. So let us now see why the value of output for this example is 121. So if you remember, then in the problem the cost of the tree rooted at some vertex v is defined like this. So let us now find the cost of the tree for this vertex 1, right? So we will calculate it like this, that first we will go from this one vertex to all of its children. So from 1 we can go to either 2 or 4 or 5. So we will go them one by one. We are going from 1 to 2. So we are covering just a distance of 1, right? So in order to calculate the cost, what we will do, we will simply multiply the distance with the value which is present on the vertex, that is the child that we are reaching at. So let me also mark up these distances on the edges. So all edges are having a edge weight of 1 only, right? Each edge will contribute to a distance of 1 only. When we were moving from the vertex 1 to the vertex 2, then the cost of the tree will be added as follows: this 1 into this 4. So 1 into 4 plus, when we moved from the first vertex to the second vertex, this distance that is took to reach 2 from 1 into the value that is present at the child. Similarly, if we have moved from first vertex to the third vertex, then the total distance would have been 2, right? So that distance into the value that is present on the vertex that we are reaching with this distance, that is 1. So 1. Similarly, we will do it for every other vertex that is present in the subtree of this one. It would be equal to 47. So as you can see now, when we calculated the cost of the tree rooted at vertex 1, then we got 47, but the output is 121. So it means that when we are calculating the cost of the tree rooted at this vertex 1, we are getting a value which is less than the value that we can get when this tree is rooted at some other vertex, right? So it means that this tree can be rooted at some other vertex other than 1, and for that vertex, when we will calculate this cost of the tree, we will get 121, but still we don't know what that vertex is, right? I hope you understood whatever I told you till here. So now if I tell you that we will get this 121 value when we will root this tree on this vertex 3, right? So if this tree is rooted with the vertex 3, then we will get 121. So let me do that for you. So when the same tree will be rooted at the vertex 3 having a value 1, then it will look something like this. So now if we try to calculate the cost of the tree, it would be 1 into 4 plus, so 2 into the value that is present on the vertex, that is 9. Similarly, we will continue to do this for every other vertex present in the subtree of 3. So we will get this, right? And when we calculate this, we will get exactly 121, right? So this is the output that we wanted, and this is also the given output in the question, right? 121. And this is the maximum that we can get for any vertex if rooted at that vertex, right? So that's why for this example the output is 121. You can try the same for every other vertex and you will realize that this is the maximum that we can get. So this is the second example given in the problem. So in this example we just have one node which has a value of 1337, and the output expected for this example is 0. In this example there is just one node, so it means that from this node it is not possible to go to any other node, so it will stay where it is. To try to calculate the distance of this first node to itself, then it would be 0 into 1337, that is the distance to itself into the value present at itself, that is will be 0 only, right? So that's why it is 0 for this example. Now I have explained you both the examples given in the problem. Let us now try to figure out how we will solve this problem. So if I tell you now that there is one another version of this problem present on the CSCS problem set. So let me show you that problem. So this is the problem present on the CSCS problem set, and this problem is actually very similar to the problem that you are right now solving here. So let me explain you first what this problem has asked, and once we are able to figure out how to solve this problem, it will become for us very much easier to solve this problem, right? So let us now try to understand what this problem asked and how we will solve it. So if you remember, then in the previous problem, what we were doing, we were going from the root node to every other node and were multiplying the value present at that node, right? But in this problem it is a little simple one. So what we have to do here now, suppose the vertex is again rooted at 1 only, so if we try to go to every other vertex present in the subtree of this one, then the cost for this tree would be like, when rooted at this vertex 1, it will be equal to the distance that us took to reach 2 from 1, right? And we don't have to multiply it with anything. If you want to multiply, you can just multiply with 1, but we don't have to do that. Plus the distance that we traveled to reach 3 from 1, that is again 1 into 1, plus the distance took us to 4, which is 2 here, that is this edge, right? So 2 into 1, plus similarly the distance that us took to reach 5 from 1, that is again 2 into 1. So if you sum this up, then it would be 1 plus 1 plus 2 plus 2, it is 6, right? You saw that when this tree is rooted at vertex 1 and we calculated this term, we got 6. And the same thing is asked in the CSCS problem statement, but instead of this just one root, it has asked to calculate this for every other root. So if you try to calculate it for 2, 3, 4 and 5 when rooting at these vertexes independently each time, then you will get the following values. So you will get these values, right? So when it is rooted at 1, we were getting 6, right? When it will be rooted at 2, we will get 9. Similarly, when it will be rooted at 3, we will get 5, and then 8 for both 4 and 5, right? So in the problem, we just have to print these integers in this problem. So I hope how this example worked and how the output is this for this problem tree distances 2 in the CSCS problem set. So as you can see now that this problem is very much similar to the previous problem on the codeforces. The only difference is that here we are going to a particular node and also multiplying the value of that node which is present at that vertex, right? So as I told you that we will first solve this problem, and once we are able to do this, we will solve the previous problem by just using the concept that we will use in this problem with a minor difference. So let us now proceed with solving this problem. So since the problem has now asked us to calculate the same thing for every other vertex, so what you can do now, since we have calculated it for vertex 1 and got 6, so you can do the same thing one by one. Like you can start your DFS call from 2, right? And just calculate the same thing. Then again you start a fresh DFS call from 3 and then 4 and then 5 each time. And as you can see that when each time we are calling a DFS call, it is going through every other node, right? When we started the DFS call on 1, then we went to 2, then 3, then 4, then 5. So it was taking O of n time when we were starting a DFS call from each node. And since now I am telling you that in order to print this, what you can do is by the brute force method, you can just do the same thing for every other node. So it would be like O of n into doing it for every other vertex, so O of n square, right? So this will give TLE because the constraint in the problem is like it is going, if you see, then it is going 2 into 10 to the power 5, so it will definitely give a TLE. So we can't do this, right? Hope everything is clear by now. So now you know that you cannot do brute force, because if you do brute force, then you will give a time limit exceeded. So how we will solve this problem for every other vertex? But before proceeding ahead, let us first see how we will calculate this 6 algorithmically. यहाँ तो बस दिख रहा था कि यहाँ जाएंगे तो इतना होगा, यहाँ जाएंगे तो इतना होगा, तो ये आएगा, लेकिन इसको DFS से कैसे कैलकुलेट करेंगे एक्चुअली में, वो पहले देखते हैं. उसके बाद देखेंगे कि सारे वर्टेक्स के लिए कैसे निकालना है. So now suppose we want to calculate the cost of this tree when rooted at this vertex 1, right? So we saw before that when we calculated for the vertex 1, we got 6, right? So what we will do now is, for each of the vertex present in this tree, we will calculate its subtree size, right? So we will maintain an array subtree size which will be holding the value of the subtree size for every of those vertex. So let me declare that array here. So this is my subtree size array consisting of 5 vertices, and if you see, then every leaf node present in this tree, right, every leaf node has a subtree size of 1 only, because 2 is consisting of just itself, 4 is just consisting of itself, and similarly 5 is also just consisting of itself. So we can say that the subtree size for the leaf vertices, that is 2, 4 and 5, is 1 only. So we will mark this here, and along with this subtree size array, we will maintain another array, let us say cost, right? So cost, and it will also be of the size equal to the number of vertices. So this is the cost array. I will very soon tell you how this will help us calculating the required thing. So initially every value present in this cost array will be 0, right? So as I just told you that we will calculate the subtree size for every of these vertex. So how we will calculate them? So if you want to find the subtree size for 3, then what I will do, I will simply combine the subtree size for, and one thing that I forgot to tell you is, instead of marking the subtree size 1 for just leaf vertices, I will simply mark them 1 for every vertices, because every vertices will have a subtree size of at least 1 consisting of itself, right? So instead of marking it just for the leaf nodes, I will mark it for every other node. So for this array, everyone is present initially equal to 1. I hope that makes sense. And for this array, it is equal to 0. So what does this cost represent? It simply represents the distance that we want to calculate, right? That is the these much values. Instead of writing this as cost, I think I should better write it as distance, because it ultimately represents what? It represents the distance that we want to calculate for every other node, right? So distance. Then we want to update the subtree size for every vertex to its true value, because it is clearly visible here that the subtree size for 3 is 3, 4 and 5, that is 3. So the subtree size for this 3 should be 3. But how we will find this? So we will just combine the results of its children with itself. In order to calculate the subtree size for this third node, we will combine the results of its children node with itself. So I will say that the subtree size for the node 3 will be equal to the subtree size for the node 3 whatever present in itself, plus the subtree size of its children. So since there are two children, 4 and 5, so I can say that the subtree size of 4 plus subtree size of 5. So if you calculate this, then for 3 it is equal to 1, and for 4 and 5 it is also 1, so 3. So that's why the subtree size for 3 is 3. So we will update this subtree size to 3 here instead of 1, and also in this array. So it is 3 now, right? Now the subtree size is holding correct values for the leaf nodes and this third node. The only vertex that we want to update to its correct value is this first node, because still if you see, then the subtree size for this one is actually 5 and not 1. So how we will get this 5? So as I just told you that the subtree size for a node, since here 1, it will be equal to the whatever the value already present in itself plus the sum of its children's subtree sizes. So here since it is 2, so we'll write subtree size of 2 plus subtree size of this third node. So since ss of 1 is 1, so it will be 1 plus subtree size of 2 plus subtree size of 3. So what is it? So it is 1 and 3, right? 1 and 3. So 1 plus 3. So what it is equal to? It is 5 now. So that's why we will update the subtree size of 1 to 5, right? So in this way we calculated the subtree size for every vertex for this tree when we started our DFS call from 1. So it has went like from 1 to it went to 2, and then from it again come to 1, then go to 3, then go to 4, then come back to 3, then go to 5, then come back to 3, then come back to 1, and then finally end, right? So this subtree size is now correctly holding the subtree size for every vertex very correctly. For 1 it is equal to 5, for 2 it is equal to 1, for 3 it is equal to 3, for 4 it is equal to 1, for 5 it is equal to 1. And since ultimately we wanted to calculate this distance array, right? So we will use this subtree size array now in order to calculate this distance. But how? And also the initially every the cost, that is the distance, for every vertex is set to 0, right? Because it makes sense, because if we start from a leaf node, then we cannot go anywhere. Since we cannot go anywhere, it means that the distance would be 0. So for 2, 4 and 5 the distance is 0 marked, right? Okay, so now it means that this c equal to 0 for these leaf nodes are correct. These are correct, we don't have to update them anywhere. So what we now want to calculate is the correct distance value for this 0, that is correct distance value for this first vertex and third vertex, because they are still not correctly marked. So now if you see here, then this 3 is equal to 0 now. But this, is it the correct method to calculate the distance value for this third node? I don't think. Along with this adding the distance value for every child node including itself, also add the subtree size for its children's. So since there are two children 4 and 5, so I am saying that also include the subtree size for each of these children. So if I include the subtree size of these children, we will get distance of 3 0, right? Distance of 3 is 0 set, distance of 4 and 5 is also 0, and including this I just told you to include the subtree sizes for the children's. So the subtree size for 4 and 5 is 1 1, so 1 1. So now we will get 2. And now if you see, then the correct cost value for this 3 should be 2 only, because if we treat this as the root now, right? So the current vertex is the root, so the current vertex is always treated as the root. So we will go from 3 to 4, which will have a distance of 1. So 1 into 1 plus we will again go from 3 to 5, so 1 into 1, that is 2, which is same as this. So that's why whenever we will be calculating the distance for a particular current vertex, we will also be including the subtree sizes for all of those childrens, including the cost for those childrens, right? And in case any one of you is wondering why I am using this formula in order to get the result for the current node, so it is very intuitive. See, suppose we are currently present at the second node, so this is our V, right? And from this second node we want to go to its subtree. So in the distance array for 2, it can go from 2 to 3, then from 2 to 4, and then from 2 to 5, and each will have a distance of 1. So 1 plus 1 plus 1, that is 3. So in the distance array for 2, it will hold the value of 3. I want to calculate it for 1, the same thing. So if I draw it very precisely, then see what happens. So initially when I went from 2 to its subtrees, that is from 2 I went to 3 like this, from 2 to 4 I went like this, and from 2 to 5 I went like this. So these 3 edges were used once, right? And so we got 3. But now if I want to move from 1 to 3, then 1 to 4, then 1 to 5, and then 1 to 2. So what happens? See, from 1 to 2 I will go, and then also I will go from 1 to 3, and then I will go from 1 to 4, and then I will also go from 1 to 5. By doing this, I am using a distance of 1 plus 2 plus 2 plus 2 every time. So that's why it is 7, right? When we were calculating the distances for the first vertex, we can actually do it by utilizing the values of its child, that is 2. How? So understand it like this, that when we moved from the 2 to 3 to 4 and 5, Then we utilize this edge and this edge. The leaf nodes distances from this one now actually consist of these three things, right? So it consists of these paths, but we know that when we were calculating it for the second node, we have already calculated for these edges, right? And the result of these edges is stored in the second vertex. So that's why I can write this term like, see, this is 1 plus, I can write it as 1 plus 1, 1 plus 1, and then again 1 plus 1. These three ones edge units, right? And now you must be wondering what does these three things are. So if you see, then the remaining term is 1 plus 1 plus 1 plus 1 only. So let me mark this with another color so you understand better. So the remaining terms are this, and we saw that this is the nothing but these distances, right? So what does this pink thing represents? Pink values represent. So if you sum up the pink values, you will get 1 plus 1 plus 1 plus 1, that is 4, and 4 is nothing but the subtree size of 2. So that's why when we were calculating the distance for the current node V, suppose the V is this now, right? We are calculating everything for V now, 1 now. So that's why we were adding the distance value of the child, that is the distance value of 2 plus the subtree size of 2, because this represents the subtree size of 2 now, right? And these red values represented sum of 4, which was nothing but a distance of 2. That's why by adding them I will always get the correct value for the current node V. So I hope you understood why using this formula would help us in calculating the current distance value for every node each time, right? So now the cost for this 3 is 2, right? So let me update that here. Cost for this 3 is 2. Since we have got correct values for 2, 4, 5 and 3 now, we just want to calculate it for the first vertex. So as I just told you that in order to calculate this distance 1, distance value of whatever it is present here initially plus the distance values of its children, so that is distance of 2 plus distance of this 3, and as I just told you, we will also be adding the subtree sizes, then we will only get the correct cost or the distance value for the current node, right? That is the subtree size of 2 plus subtree size of 3. And if you calculate this, then you will get distance of 1 is 0 initially, and distance of 2 and distance of 3 are 0 and 2 respectively, and the subtree sizes of 2 and 3 are 1 and 3, right? So if you sum this up, then you will get 2 plus 4, that is 6. So the correct cost value for the first node is 6. So let me update that here also, right? And just before I told you that whenever the final distance array would have been calculated, the first value, since we have started our DFS call from 1 only this time, so that's why the value that is present at this first index will match our answer. So now in this way we have successfully solved this problem for the first vertex, but as I told you that instead of doing it for just the first vertex, we want to do it for every other vertex. So you can use the same logic by starting the DFS call from every other vertex every time, right? But as I told you, it would give you a TLE. So as I just told you, we will use a DFS starting from 1. So we will call a DFS for 1, and initially I will consider -1 as its parent, right? And in the DFS call, I will continue visiting each of its children until we reach the leaf node, and we would have set every value to the subtree size equal to 1 initially, and every value in this distance are equal to 0, right? Suppose V is the current node, so I will set subtree size for this V equal to 1 every time, the distance for this V equal to 0. Meanwhile, we will be visiting its children's. So suppose C is the child now, and I will just say if C is not equal to parent. So we know that this is how we do a DFS in a tree, right? We don't have to use a visited array, instead we just use a parent. So if C is not equal to parent, then we can again call our DFS function from this child node, and this time the parent of this child node would be the node that we just came from, that is V. So this. And after doing this, I just told you to combine the values for the current node with its children nodes, right? So I will say that the subtree size for the current node, that is V, would be equal to the value whatever it is present at it initially, or the current value, plus the subtree size of its children, that is this. And I also told you once we have calculated this, I will also calculate the distance for this current vertex, that is v, and it would be equal to the whatever the current value it has holding plus the value that is present in its children, that is this. And just by doing this, I think we would have been able to get these two arrays, that is the subtree size and distance array, right? So I hope now you understood very well how you can calculate the required value by doing a DFS call from each one of these vertices, right? Okay, now you know that we will get the correct value when we will start a DFS call from each one of these vertex, but this thing will be costly for doing for every other vertex, right? Can we do something better? Can we use the values that we calculated when we started our DFS call from 1, use these values in order to find the values that would have been present in these arrays if I have started a DFS call at this 2, right? So what I mean is, I don't want to recalculate everything for the 2 array when I start a DFS call from each one of these vertex. I just want to use this previous information in order to calculate the new one. So it is like memoization in dynamic programming if you have studied. So in order to do this, we have a very beautiful technique present in this TP on trees problem, and it is called as rerouting technique. Right. So we will use this technique in order to modify this array in such a way that we don't have to calculate it over and over again for every vertex, but using just the previous information in order to calculate it for every other vertex. So as the name suggests for this technique, that is rerouting. So it clearly means that we would be rerouting our vertices every time. That is, if initially we have considered 1 as the root of this tree, then in the next time we will consider 2 as the root, and then in the next time we will consider 3 as the root, then 4 as the root, then 5 as the root, right? So this is my old tree, right, which is corresponding to these 2 arrays, right? And now I want to recalculate, and now what I am telling you is, since I want to calculate it for 2 now, right? So now I want to treat 2 as the root vertex, and I want to start a DFS call from 2 instead of 1. So when 2 is treated as the vertex, then the tree will look something like this. So 2 is the vertex now, and 1 is its children, and 3 is, and the subtree of 1 will remain as it is, right? So now I want to convert this tree, right, this tree into this tree. And when this tree will be converted into tree like this, then obviously the subtree size of some of the nodes will be changed. For example, earlier the subtree size for 2 was 1 only, consisting of itself, but now if 2 is treated as the root vertex, then the subtree size will be increased by this much vertexes, that is the subtree size of 1. So the subtree size of 1 will have been added to 2, right? And also before, from 2 we were not able to go anywhere because it was a leaf node. But now if you look, then from 2 we can go to 1, we can go to 3, we can go to 4, and we can go to 5, because it is the root vertex. Now we can go anywhere in this tree. So it means that whatever the values that are present in these 2 arrays, it was for this tree only, right? But now these 2 arrays will also change corresponding to this tree. So now if I want to derive a tree consisting of 2 as the root vertex from this tree which has 1 as a root vertex initially, then first I have to end the relation of this one from this 2th vertex. Why? Because right now this first vertex is also holding the value of subtree size of 2, which is 1 here, and also the distance value of this 2. So both the subtree size as well as the distance values for this second vertex is contributing to the values of this first vertex. But since now I want to treat this tree independently, right? So for that I have to first end the relation of these 2 with this one. So what I will do simply is, in these 2 arrays, since the subtree size for 2 was 1, so I will just subtract this 1 from the subtree size of 1. So the subtree size of 1 is 5 initially, so I will subtract 1 here. So now it will get 4, and now I will also subtract the distance value, that is 0, from this 1. So if I subtract 0 from this 1, that is 6, so 6 minus 0 will be 6 only, so it will be 6. So now it means that these 2 arrays are now not corresponding to this tree, no, but instead these 2 arrays are now corresponding to this tree only. You can match them up also, because, and yeah, I forgot to do this, the subtree size of 1 has become 4 now. That is, it only corresponds to this part and does not include 2 anymore, right? And one more thing that I think I forgot to tell you, it's important, that it's very important actually, that when we were calculating the distance for this vertex, we were adding the distances of its children, right? But here we also have to include the subtree sizes of its children, right? So this is a very important point. We have to include the distance of the children as well as the subtree size of the children, then only we will get the current distance for the current vertex. So here also, since I am ending the relation of 1 with this 2, so in that case the subtree size of 1 would have decreased by 1, so I decreased it by the subtree size of 2, so it became from 5 to 4. And since the cost of this one also included the cost as well as the subtree size of this 2, so now I will decrease 6 by the sum of the subtree size as well as the cost for this vertex 2. So it will be 0 plus 1, that is 6 minus 1, that is 5. So now the distance for the first vertex will become 5. And now if you see, then I think, so by doing these, like ended the relation with 2, right? So it doesn't correspond that this edge does not exist anymore. It do exist in the adjacency list, but in terms of values, I have no relation with 1. So it means that for whatever the values are present now for 1, it has only used the values present in this subtree and not this anymore. And since now I have subtracted the values of 2 from 1, now you can view them, these two subtrees, as independent actually. And now what I want to make these 2 as the parent of 1, that is 1 becomes the children of 2, then only my 2 will be treated as the root vertex for this tree, right? So what does this mean? The subtree size of 2 will increase by the subtree size of this 1, right? And also the cost value for this, or the distance value rather, for this second vertex will also include the distance value of this first vertex, that is the child, and also the subtree size of this vertex, because this is how we are calculating it for the current vertex. Because now the current vertex our is 2 and we want to calculate it, so we will use the values of its children. And since now 1 is acting as the children of 2, so I will be using both of the values of this 1 in order to calculate it for 2, right? So I will just do the same thing in the subtree size of 2. So the subtree size of 2 now will be what? So whatever the value is present in the subtree size of 2 initially, that is 1. So and initially it consisted of itself, and now I have to add the subtree size of 1. So the subtree size of 1 is 4, that is this one. So I will be adding this here only, right? So 1 plus 4, that is 5, that is the subtree size of 1. So it will become equal to what? So 1 plus 4, that is 5. So let me update this in the array. So the subtree size of 2 now is not 1 but 5. And also we have to update the distance value for the second vertex, because now since 1 is the child, so it will be using its values of both the subtree size as well as the distance in order to calculate its own value, right? I will say that the distance for this 2 is whatever it is holding currently. So initially it was holding 0, right? So the current value, that is 0, plus now the distance value present at this child, that is the distance of this one. So it would be 0 plus distance of 1. So what is distance of 1? It is 5. So it would be equal to 5. So I will update the same thing here in the distance array as well. So distance of 2 is now 5 instead of whatever it was present before. And now if you look, then these two arrays are very much correctly representing these three, right? And not this anymore. So we have successfully converted this tree into this tree, and whatever the value is present in the distance array for the second vertex now is the value that we wanted to calculate actually, right? Because if you see, then if I try to go to every other vertex from 2 and calculate the distance, so the edge weights are 1 only. So from 2 to 1 it is 1, plus from 2 to 3 it is 2, plus from 2 to 4 and 2 to 5 it is 3 each, so 3 into 2, so we will get 3 plus 6, that is 9, and this is now correctly stored in the distance array as well. I think by now you must have realized that just by using the previous information we derived the correct result for this second node, and not by doing a complete DFS call. Instead, just by removing the connection of this one from two in its arrays, and then again adding the result of the remaining tree, that is this tree, back to the 2, right, and thereby getting the full tree completely. So this is how the rerouting works. So we change the root of the tree by first removing the child from this parent, right, through these arrays, and again adding this remaining subtree of 1 back to 2, thereby making 2 as the root of this tree, and whatever the values that are present in these two arrays now correctly represent the values that should be there for this subtree, or rather the tree which is rooted at the vertex 2. And in the very similar way, for how we did for 2, right, we did it for 2 by coming from 1, so we will do the same for 3, then 4, then 5, and for every time we visit a child we will get the exactly same array for what we need for the current tree for each one of these child. So in this way we don't have to again and again call DFS for each one of these nodes, but rather just calculate it for one time for the first node, right? So we calculated it for this tree once, and then we just did a last DFS call, that is the second DFS call rather, and in the second DFS call only we were able to get the correct arrays for each one of these vertices when treated as the root, right? And in this way we calculated the current arrays and thereby able to get the correct value of this distance for each one of them every time. We were getting 6, for 2 we are getting 9, for 3 we were getting 5, and for 4 and 5 we were getting 8. So 6, 9, 5, 8, 8 is the thing that we wanted, and we have calculated this just by using two DFS calls. And if you see the output for this example in the problem, then it is exactly 69588 only, as you can see, right? So I really hope that you understood how we solved this CSCS problem tree distances 2 in order to calculate the sum of the distances from every node to every other node, but not by doing multiple DFS calls, but just by using two DFS calls and by utilizing the results of the first DFS call into the second DFS call. Thereby this is, and since we are utilizing the results of the first DFS call, that's why it is a question of DP, because we are using the previous results, that is memoization technique, right? Now I think we should move to the original problem, that is the code forces problem. But as I told you that problem was exactly similar to this problem with just a minor difference. So let us get back to that problem. So if you remember, then this was the original problem from the code forces, and this is the results that we wanted to get. So let me now explain you the same thing that we just discussed before with a short example in meantime. So consider this example in which there are 5 nodes, and also we are given with a value associated with each node, right? And each edge weight has a weight equal to 1. So you know this. So since in the problem statement we are asked to find the maximum possible cost, so what we will do is we will simply calculate the result for every vertex, and then at last we will maximize the result. So in the similar way, just before as we derived this array, if the CS problem has asked us to find the maximum instead of just finding it for every node, then we would have just simply returned 9 instead of this whole array. So the same thing we will do in the code forces problem also. Here we will find this array and we will just return the maximum out of it, right? So you know that this problem is a little different from the actual problem, because in the before problem we were asked to just calculate the distance from each node to every other node, but here we don't have to consider the distance. For example, if we are moving from 1 to 2, then we have to consider a distance multiply the value that is present at the child node, that is 543, right? So if we started our DFS call from 1, then we'll go to 2, then we'll go to 3, then we'll go to 4, then we'll go to 5, and we will get ultimately 43, right? So how we will calculate this? So I will just do the exact same steps as we did above for the problem. So what I am saying is just maintain two arrays again. So this time I will be maintaining two arrays, and let me give it the name as subtree sum, and again the same name, that is the distance array for the second array, and both would be of the size 5 only, that is the number of total vertices, right? So before I was maintaining the subtree size array because it was holding the subtree size for every node, but now instead of using the subtree size I will use the subtree sum array. So it clearly means that instead of the subtree size, it will now hold the subtree sum for each vertex. So for, as you can see, that for the third, fourth and fifth vertex, the subtree sum is 8, 7 and 4 respectively. So for the third, fourth and fifth, it is 8, 7 and 4 respectively, right? And for 2, if we look, then the subtree size is what, subtree sum rather is what? So 8 plus 7 plus 4 plus 5. So it would be equal to, 24, and the subtree sum for 1 would be equal to the sum of every value present at every vertex. So it would be 24 plus 2, that is 26. So this is our correct subtree sum for this tree rooted at vertex 1 initially, right? And now we also want to calculate the distance array. So just as we did before, so if you remember what we used to do, in order to calculate the distance value for the current node, whatever the value was present initially, earlier we were just adding the value of the children's plus the subtree size, but now instead of subtree size, just use the subtree sum of the children, right? So here if you see, then for distance 2, and since the DFS call would be propagating like first it went from 1 to 2, then from 2 to 3, then from 4 then to 5, then it would be combining the results of these children into this and the result of this into this finally. So it would start from the bottom to the top. Since the distance of 3, 4 and 5 is 0 only initially, right? So when v is 2, that is we are currently present at this node during the backtracking, so it will combine the results of its children now. So I can say that the distance for this 2 will be the summation of whatever the value initially present in this node plus the distance of each one of its child as well as the subtree sum of its children, exactly same as we did above in the previous problem. So what it would be equal to, so since distance of 2 is holding 0 initially, right, so every element is 0 initially, so 0 plus the distance values of its children, that is 3, 4 and 5, which is 3 zeros only, plus the subtree sum of its children, that is 8, 7 and 4. So 8 plus 7 plus 4. So if we calculate these values, then it will get ultimately 8 plus 7 plus 4 only, which is equal to 19. So distance of 2 has become 19 now, and it is true because if you try to go from 2 to deep down its subtrees, then you will get this value only. See, 1 into 8, 1 into 7 and 1 into 4, just add them up. So 8 plus 7 plus 4 equal to 19. And now we have got the correct result for this children, and now we will utilize the results of this children in order to calculate the value of this thing. Our current v is equal to 1, so for distance v equal to 1 would be equal to the current value of distance 1, right, plus the value of its children and the subtree sum of its children. So what is the current value? So current value of dist of 1 is equal to 0 only, right? And then we will add the distance values of its children, since here it is only one children, that is 2, and its value in the distance array is 19 now. So 19 plus the subtree sum of 2. What is the subtree sum of 2? It is 24. So on adding them up, that is 19 plus 24, we'll get 43. Let us verify that if it is correct for node 1, right? So suppose I start from 1, then I will go to 2, then 3, then 4, then 5, and keep on multiplying the distances with the values. Then I will get, for this node I will get 1 into 5, for this node I will get 2 into 8, for this node I will get 2 into 7, and for this node I will get 2 into 4. So this would give 16, this would give 14, and this would give 8, and this will give 5. On adding this 16, 5, 14 and 8, On adding them up, see what we get. So we exactly get 43. We are exactly getting 43, and before also we calculated and got 43 only. So it means that our arrays are getting updated correctly. So now if I update the distance array now, it is 43 now. And I think it has got little messy, so let me erase some of the things. Okay, so now I have redrawn the things little bit clearly and erased unnecessary things. So this is the formula that we just used to calculate the values for each node and updating the resulting arrays like this. This array corresponds to this tree, right? This array corresponds to this tree completely. And you can also match the values of this array with this tree and you will get exactly this, right? But if you remember, then in the previous problem, I just told you that whatever the root of this tree is, if you try to find the distance value of this root in this distance array, then this will only be the right one, right? Because this is the thing that we just calculated when everything was treated as its subtree, because we visited every other node from this vertex. But the distance value of 2, if you look here, is 19 only, because this 19 corresponds to this subtree and not the complete tree, right? So whatever the root of the vertex is present currently, it was only the distance array value is only correct for that, and the remaining values are true for only their subtree, because the subtree of 1 is the whole tree. It means that from 1 we are visiting every other node, and in the question it was asked to us to visit every node from the current node, and it is only possible when that node is present as the root vertex. So that's why this distance value of 43 is true for this. And if it is equal to 19 for the second vertex, then it is only considering this subtree and not the complete tree. But as you saw in the previous problem, that we can make this 2 as the root of the vertex by using a technique called rerouting. Similarly, we can also do the same for 3, 4 and 5. So we will do the exactly same things one by one. So this is the codeforces example type. I've taken this by myself. So let's see how that same formula will work here also. So suppose we are currently standing, suppose we have done the DFS call and currently we are standing at this node 2. So this is our V, right? So in order to calculate the distance for this 2, I have to add the distance of this child and the subtree sum of the child instead of subtree size as we did before, right? So now let's see how this formula is working actually. So when we considered this 2 as the V, then we calculated the distances like this. See, we calculated it like 1 into 8 plus 1 into 7 and then 1 into 4, right? Right. And then when we were calculating it for 1, when V is 1, then it was like 1 into 4 plus 2 into 8 plus 2 into 7 and then 2 into 4, right? So if we try to simplify this a bit, then see what happens. So this is a separate one, and this is nothing but 1 into 8 plus 1 into 8, right? Similarly, this is also nothing but 1 into 7 plus 1 into 7. Similarly, this is also nothing but 1 into 4 plus 1 into 4, right? So now if you compare, then 1 into 8, 1 into 7 and 1 into 4 is same as this, right? So what does the remaining value represent? That is this. These are the remaining values, right? So if you sum up these remaining values, then you will realize that this is nothing but the subtree sum only of the child. And what does the pink values represent? It represents nothing but the distance of the child. So that's why this formula will again work here. That is, the distance of V would be the summation of the child for both the distance and the subtree sum. So this is equal to what? This is equal to 23. And what does this is equal to? This is equal to 19. And you can see that very clearly that the subtree sum for the 2 was 23 only and the distance for the 2 was 19 only. And thereby adding these two terms will give us 42. That is the distance of the current node V. So that's why we were taking the distance of child and the subtree sum of child whenever we are present at a current node V, and we will do this for every child. So this is the previous problem that we solved using rerouting, if you remember. So what we were doing, we were just modifying the arrays, right? We were subtracting the values of the children from the parent first, and then again adding the remaining values of the parent to the children, and thereby getting the final tree. But since we want to do it for every children, so make sure that after doing this and deriving this arrays, since I want to treat 3 as the children thereafter, and then 4 and then 5, then I have to make sure that before doing the same thing I again have to come back to this tree, right? So it is like, first I will be reducing the value of the children from the parent and thereby getting this tree, and then again adding the remaining value to this tree in order to get this tree, and then I just have to do the opposite of what I just did. So then I will get back to this, and then I can do the same thing for other vertices as well. So I hope you understood. The same thing will be done here also. So since in this example 1 was considered as the root initially, and I want to treat 2 as the root now, so just do whatever I told. So what I told, I want to treat 2 as the root. So if 2 becomes the root, then the tree will look something like this. So when 2 is treated as the root now, the tree should look something like this, right? And in order to do this, I just told you that we don't have to do anything with the adjacency list because the connections are not getting changed, but what is getting changed is the values that are present in these arrays. So I will just modify these arrays again. And why we are doing this, we are doing this because we do not want time limit exceeded in our brute force method, because the same thing that we did for the first vertex we can do for every other vertex in the very same way by starting a DFS call from every other node, but that would give us a O of n square. So we are just want to utilize this arrays, right, these arrays, in order to calculate the correct value for each and every other vertex, just as the previous problem. So now if you see, then what I told you that in order to make 2 as the root, I first want to break the link, right? That is, I don't want to store any information of 2 in this one now. So for that I will subtract the values of 2 from this one, because this one is made up by using the subtree sum as well as the cost value of this 2, right? So in this array I will say, for the first index, that is the first node, I am removing the link of 1 with the 2. So whatever the values are present in the subtree sum of 1, which is 26 here, so it would be now 26 minus the subtree sum of 2, that is 24, so it would be 2 only. So let me update that to 2 here. So subtree sum of 1 will become to 2 now. So you can imagine it like this is now a separate tree and this is a separate tree, and since it is a separate one, the only subtree sum is itself, which is equal to 2, that's why 2. And along with updating the subtree sum, we also have to subtract the distance also. So I will say that the distance of 1 would be what? So whatever the current value of distance is, so the current value of distance 1 is 43, right? Subtree sum for this 2, which was 24, plus the cost of this 2, which was 19. And once I have subtracted that, I would just have got 0. So it would have been 0 only. So it would have been 0 only. And it is true, because if we have separated these two as independent trees, then from this tree we would not be able to go anywhere, right? Because it is consist of a single node, and that's why it would be 0. So I think now this is the correct values. You can match them up also. Now our work is not done yet, because right now we only have removed the link of 2 with the 1, but we again have to add this tree to this, and this will now point like this to look something like this. And in order to do that, I will just add the result of 1 to 2 again, and if I do that, see what happens. So in the 2, I want to utilize the results of 1, so we will modify this 2 values. So the subtree sum of 2, which is currently 24, will also include the subtree sum of 1, which is 2, so it will become 26. And also the distance for this 2, which is 19 here, will include the distance of 1 as well as the subtree sum of 1, which is 0 plus 2, that is 2. So 19 plus 2, 21. So this will be 21 now. So now if you see, then this array represents this tree correctly, that is the tree when rooted at vertex 2. And since we wanted to find the answer when rooted at vertex 2, so you can see in the distance array it is equal to 21 here only. And if you try to calculate also, see, 1 into 2 plus 1 into 8 plus 1 into 7 plus 1 into 4, then 2 plus 8 plus 7 plus 4, so it is equal to 21 exactly. And Thus we got it in this way, by just applying the rerouting technique to the original node one by one and doing it for every child, and thereby getting the current distance array and subtree sum array each time. So in the same way that we visited from the first node to the second node and did it for the second, similarly we'll go to the third and then we'll do it for the third node as well, then for the fifth node and for the fourth node and for the fifth node. So in this way we will do the same thing for every other node, and each time we will just maximize this result. So we'll take a maximum of this result for every time the function gets called, right? So I am right now hoping that you understood what I told you about this problem. So it got a little lengthy, I know, but it was important to tell you because it consisted of mainly two problems. First from the CSCS problem set, and we just saw how we used that the same thing and applied to this problem and got the same results that we wanted, right? So I think now I should write the code for this problem, and in the code it will become very clear to you how we will do this. Don't forget to keep updating this tree back to this tree after every time, because since we went to this tree from this tree, now if you want to do the same thing for the third root, right, when 3 is treated as a root, then we will do the same thing by coming to this tree. Thereby every time we modify the tree, we have to modify it back, and then only we can go and treat some other vertex as the root then. So let us now go to the code editor and see how this will be coded. So if you look in the problem, then initially I have to take the input of n, then n integers, and then n-1 lines, right? So let me start by taking the inputs. So first I will take n and then n integers, right? And for each of the n lines I will be let's store the value of each node in a vector called as value. So let me declare that here also, and whatever the total number of nodes can be there, so since it can go up to 2 into 10 to the power 5, so let me say it as 2e5, and since I'm using one based indexing, I'm adding a 1 extra, right? So I have taken the input for the each of the vertex values, and now I have to take inputs of n-1 lines. Of the lines consist of two integers, that is u and v. An adjacency list, so g of u dot pushback v. We declare this adjacency list globally, so vector int g, and again it will be of the side maxn only, so like this, right? After I have taken all the inputs, what I said that we will just start one DFS call from first vertex, because I am pre-calculating the values, not exactly, but let me name it like this, and we will utilize this result. And I will start it from the first one, and the parent of 1 is initially -1, because the root is having no parent in the tree, right? So you can give it 0 also, but I gave it -1 instead. And now let me write down this pre-calculation. So what I said you to maintain 2 arrays every time. So I will be maintaining 2 arrays, and it will also be of the size maxn only. Similarly, there will be another array, since it is storing the distance, so let's name it distance, and it will also be of the size maxn only. I also told you that initially the subtree sum for every vertex would be equal to whatever the value is present in it initially, right? Sum for this current node would be equal to the values that is present in this node, right? And also I told you that the distance for every node would be 0 initially. So let's, even if you don't write it, there is no problem, because initially everything is initialized to 0 only here by default. So yeah, and after this has been done, what I told you to just iterate through each one of its children, right? That is the children of the present node. And if this children is not parent, because this is how we do a DFS on tree, so we will again call the same function, but the parameters now will be c and node. That is the parent of c is node now. And after, in order to calculate the value for the current node, I will do two things. That is, in order to calculate the subtree sum for the current node, I will utilize the value of its children, and we saw how it worked in the explanation very well. So it would be subtree sum of this child, right? And also the distance for this node will be whatever value is present initially plus two values, right? Two things. First, whatever the subtree sum we calculated for this child plus the distance of this child. And just by doing this, I think our pre-calculation function is ready. And now what I told you to just do a second DFS call, because in this DFS call the result is only stored correctly for the first vertex, but since in the question it has asked us to maximize the possible cost, so we have to check it for every other vertex as well. So that's why I will say let's name it reroute, because we would be applying a rerouting technique in this, and I will just start the DFS call from 1 only, and its parent would again be -1. And after doing this, whatever the maximum value, let's say it maxi will be there, I will just print that and return, right? So let's say ll maxi is 0 initially, and we have to maximize the same thing, right? So let me write down the reroute function, and we'll visit each of its child. So we will again calculate the same thing, that is reroute of C, and its parent would be node now. And I told you in the explanation that when we would be calling DFS for the second child, we would be modifying the arrays, right? And then only we would be going to this child, right? We would be storing the correct values for each of the vertex in this fashion from top to bottom only, like for the second, then 3, then 4, then 5. So just before calling the DFS function for 2, I will be modifying these arrays, right? And once I have calculated it, I will restore it back to the original array, and then I will do the same for 3, 4 and 5, right? So if I do the same thing here, since I know that I can visit this child from the current node, so I will modify the current arrays just as I told, to subtract from whatever it is storing the result of its child, that is this. And I also have to subtract the distance of this node, since it is utilizing two things of this child, that is first the distance of the child and then the subtree sum of this child, right? So in this way, I removed the link of parent from its child, right? So by these two lines, I removed the link of the child from the parent, but now I have to add the result of the remaining subtree of the parent back to the child, just as I told you in the explanation. So I will say that the subtree sum for this, I think I should better copy it because everything will be same. I just have to reverse the names, right? So instead of, in place of this node, it will be C, that is the child, and here will come the node, that is we are adding the subtree. I will add this, right, not subtract, because subtraction was done in this part, because that is removing the link of the parent to the child and then again adding the link of the remaining parent back to the child in this way. So it would be no C only, and this will be node. So just as we did this, so what has happened after doing these 4 steps? So after doing these 4 steps, I have got my modified tree, that is this tree, from this tree, right? I have got this tree from using this tree, and whatever the distance value is holding for the root, so it will be storing the correct one, right? So I just have to maximize that only, because it was asking the problem to maximize this value. So I will say that maxi is equal to max of maxi comma whatever the distance value is getting holding the current node value, right? So the same thing I did here, and I think it is dist, not dis, and use long instead in place of int, because it might exceed in some cases. After doing this, as I told you that I have to revert back to the tree from which I have come, right? So I just have to reverse the operation from what I just did here. So I will just again say that instead in place of node, I will use C, and in place of C I will just use node. So you just have to interchange the things, right? So after doing this, we are again back to the same tree from which we have come, and now we can do the same thing for other childs as well, and thereby getting the correct answer for each child every time and treat it as vertex, and that is root, and thereby maximizing the answer present in the distance array every time. So now if I try to run up the test examples, so I think our test cases are getting passed for both the input examples. So let me submit now this on the platform itself to verify the correctness of the solution. So it's finally accepted. As you can see, this is the code that we just wrote, and I explained you very well in the lecture why we did these things like pre-calculation and then just using the result of this pre-calculation in order to calculate the same thing for every other vertex when treated as a root instead of doing it multiple times, that is a multiple DFS for every root, right? And this is how the rerouting works. Like you first remove the link between the parent and the child and then add the remaining result of the parent back to the child. In this way the child becomes the root now, and then whatever the value is present in the array is the correct value for that node. And since we have to maximize that in this question, I just maximized this. And I also told you that since we have to do it for every other child, we have to restore it back to the tree from where it has came. That's why we just did the reverse operation of this 4 lines here, right? And in this way we solved this problem. Thank you very much for watching this video. I hope you understood something new. And if you really like this video, please give up a like and subscribe this channel, because it takes a lot of efforts to create each and every single video. And in the coming days I will be uploading more and more videos related to DP on trees and other advanced topics from the graph theory and dynamic programming. So yes, and if you have any suggestions, feel free to write in the comment section. I will read those comments and act on it accordingly. So yes, thank you very much for watching this video. Thank you.